Okay, good afternoon. Let's continue with chapter 2. If you have not yet read the announcement, I posted an announcement earlier. There are a couple of reading assignments and a small short homework assignment. So you have 3 days, Friday, Saturday, and Sunday to get it done. There's like 2 problems on there. So, and then some extra credit tutorials also on there. So it shouldn't take long. Right, let's see. Also, if you've not yet taken a look at the content library, there's a section called quiz solutions. So we're posting the quiz solutions on there. It's in the content library. All right. Okay, so sure. Okay, so we had stopped right here, sources and loads, and we looked at independent sources and dependent sources, right? Independent and dependent. All right, and then we're kind of a rush at the end where we pointed out that the dependency can be of 2 kinds. We can have a dependent voltage source and a dependent current source, and they could both be dependent on a voltage or a current. Okay, and so we have 4 different kinds of dependent sources: VCVS, CCVS, VCCS, and CCCS. And the reading that I've assigned, walks you through all of these sources, the different types, and the ratios and the units for of these dependent sources. Okay, so when we say independent source, what is actually happening? Well, as the name suggests, source, it is providing some energy. It is a source for energy. So it is converting energy, of course, is converted, not created or destroyed. So if you have a generator, that generator converts mechanical energy into electrical energy. If you have batteries, it's chemical energy into electrical energy, chemical reactions, electrochemistry. We also have solar cells, right? Photons transmitting their energy to electrons, so light energy. Or so sources can be of different kinds depending on what the input is. You can have mechanical, you can have chemical, you can have photons. Let's see, what else? Potential, thermal, right? So there are the very kinds of sources. Now, what do we mean by a voltage source? What do we mean by a current source? So in real life, voltage source and a current source are exactly the same. It's the same box. If you have been to a lab bench, you may have even used a power supply perhaps. If there's a power supply unit on a lab bench, it is supplying both voltage and current. They go hand in hand. Voltage and current go hand in hand, right? You can't supply current without supplying voltage. You cannot supply voltage without supplying current. So the difference is, or by its very definition, a voltage source will supply its rated quantity irrespective of the current requirement. Okay, so a voltage source will supply its rated quantity, rated voltage, irrespective of the load, irrespective of the current requirements. It'll keep the voltage constant. Okay. The current could change, but the voltage will always remain constant. Similarly, a current source is rated to supply its, current source will supply its rated current irrespective of the load that is connected, irrespective of the voltage that is required. In other words, it'll keep the current constant while the voltage could change. Okay. And so in every power supply unit that you will use, or if you have noticed in the past, there will be two modes of operation. This constant voltage mode and constant current mode. Okay. CV and CC. Okay, CV and CC. If you operate a power supply in constant voltage mode, it's a voltage source. If you operate the power supply in constant current mode, it's a current source. The exact same operation. All right, so let's take a pause. Let me know if you have any questions. When you're in the lab, be sure to ask your instructors about the settings. Every power supply unit from every manufacturer will have different ways to set the power supply. Previously, in my time, we had analog dials. So you'd simply turn the dial and set the voltage or set the current. Now you have microcontrollers in every power supply unit, so you can program it digitally, pressing a few buttons. So one of the most common ways to do that is to first set a current limit. So that current limit shouldn't increase beyond a certain point. So every experiment you perform going forward as an E, always keep in mind, you always must set the current limit for your procedure. Otherwise, you will end up blowing something out. Okay, so always set the current limit. If you're unsure, you ask your lab instructor, what is the current limit for today's lab? Okay, so always set the current limit first, because a voltage source is going to change the current while keeping the voltage constant. Okay, so if you connect a very low resistance load in there and the voltage is high, or there's a short circuit somewhere in there, the current's going to increase by an abnormal amount. So unless you set a current limit on there, you're going to blow something out. Okay. I will come back to this after we get done with Ohm's law. All right. But for now, does this make sense? If you run in constant voltage mode, it's a voltage source. You run in constant current mode, say current source. But physically, they are the same box. All right. Dependent sources. We had, sorry, not we had, just three examples. Okay. So the dependent sources, first, we want to identify what kind of source it is. So first one, what do you see inside the diamond? Arrow, plus and a minus. So plus and a minus indicates it's a voltage source. So it's a dependent voltage source. So what is the value of this voltage? 100 times I delta. So 15 milliamps. And so this gives us 1500 millivolts or 1.5 volts. If I delta changes, then your V, the output voltage being supplied by this dependent source, will also change. Okay. So these are just three quick and simple examples. How about the second one? Arrow inside, so it's a current source, yes. But the question is, what are the units? Because the dependency is on the current. The dependent source is supplying 0.25 IX. So the units, and we haven't talked about it yet, the units is, it depends on a quantity, right? So it depends on a quantity. So it's always per, meaning voltage per amps, voltage per volts, or amps per amps, or amps per volts. So here the units would be amps or amps, because it's supplying 0.25 amps or 1 amp of IX. Okay, it is supplying 0.25 amps of current for every 1 amp of IX. Hence the units amps over amps. So it's a ratio. It is dimensionless. There's no units for this second example. Okay. Make sense? Okay. Okay, how about the third one? What is Vs? What kind of source is this? It's a current source, right? It's a current source, and we are asked to measure the voltage across that current source. Short answer is, it is impossible. It's not possible. So we cannot measure the voltage across a current source. We cannot measure a current through a voltage source by standard methods. Okay, it's not possible. We have to do it via other indirect methods. Okay, so this is not possible. Whether it's independent or whether it's dependent, it's just not possible. Okay. Oh, by the way, do any of you have friends who are coming next year? Today was the visit. This whole weekend is the visit. You all, anyone have any friends who are joining you? No. No. Yeah. Did you all visit last year? Some of you did. Some of you didn't. Okay. It's always a good time. This time it was a clash, so I couldn't do a lab tour. Did you all? So if you visited last year, did you attend the lab tour? You might have seen me in the polymer electronics lab. Organic chips. Yeah. Okay, connection of sources. So this is, again, fundamental concepts to show if we connect independent sources together, whether the connection is valid or not. Okay. So two things to keep in mind. If you have a voltage source will supply its rated voltage between its terminals. So you cannot have any other voltage across those terminals. That means that connection would not be valid. Same thing with the current source. A current source supplies its rated current through its terminals. So you cannot have anything in series or in its pathway that is contrary to its value. Okay. So if you look at the first example, we have a voltage source of 10 volts that is connected between A and B on this side. And we have another voltage source connected between the same terminals, A and B, on the other side. So is that permitted? Yes, it is. If you have two connections and you have a 10-volt source on one side, you connect the 10-volt source on the other side, yes, you can make a connection like that. Okay, so it is permitted. All you would do with this is you will actually increase the amount of current that is flowing in the circuit. Obviously, this is a very simplistic situation, example, right? You're not doing this right now. How about the second one? I see a shake. That is correct, because if there is 5 amps flowing here, if there is 5 flowing here, at the same time, we cannot have 2 flowing in the same pathway. That's just not possible. So this is valid. This is invalid. Okay. Again, let's, yes. So let me understand the question. The question being asked is the voltage sources are connected with a different orientation. Oh, I see what you. No, that is actually the correct method to connect it. So, and we'll talk about series and parallel connection just a little bit in a few slides. But right now, if you take a look at the source on the left, you have a positive terminal here, you have a negative here, and then this voltage source also has a positive here and a negative here. So connecting positive to positive and negative to negative, that is permitted if they both have the same value. That's the key thing. So the answer to your question is that if they have the same value, 10 volts and 10 volts, then yes, we can connect it, because that is indeed possible. But if one of them, this is actually a very good question. If one of them was, let's say, 5 volts and this was 10 volts, that would not be possible. Because again, the property of a voltage source is that it should supply its rated voltage between its terminals. So if both terminals of both supplies are connected together, there's a clash. One supply is trying to keep the terminals at 10 volts, the other supply is trying to keep it at 5 volts. And so that wouldn't work. So that connection is invalid. Yes. Okay. So that's again a good question. So the question being asked is if we had a connection like this, 10 volts, and then we had something like this, 5 volts, polarity opposite, right? So if we connect it like this, then that would be invalid because it's trying to, well, the magnitude, that's actually a good question. It's a series connection. So series connection, the voltages will add up. So if there was a resistor or something in the middle, this would be in series. The 10 volts and the 5 volts are in series, and so they would add up. So in a way, this would be valid because the polarity is not the same. They are not trying to maintain the same polarity across the same terminals. So in a way, it's valid, but only if there's a component in the middle. If you connect a power supply directly like this, then it would not work, would not be valid. Okay. So again, to remove confusion, short answer, it would be invalid. Because if you're solely looking at these two terminals, the entire thing rests on the inherent property that the voltage source will always supply its rated voltage between 2 points. So power supply on the left is supplying 10 volts at A and B, and power supply on the right is supplying minus 5 volts between A and B, which is not physically possible. Okay. Okay, how about the third one? You have a voltage source and we have a current source. We don't know what this current is because we can't find it directly. And we don't know what the voltage is here because we can't find it directly. Sorry, this would be minus and this would be plus. But one thing we know for sure is that the current in a voltage source will always go from minus to plus. Remember, from a source, it is opposite. For all passive components, current always goes from high to low, from plus to minus. For a source, it always goes from minus to plus. So if you're a source, we mark it as negative, minus to plus. So current is flowing in the upwards direction, which is the same direction as that current source. So this connection is valid. Okay, this connection is valid. Any questions? Okay, all right. All right, we get resistance. What are you all doing in 143, the lab, the procedure? I know week one was the software, right? Fusion 360. What's on the agenda for next week? Anyone? You all don't know? Okay, all right. Excuse me. Okay, resistance is a property, comes from the word resist. The English word resist means to oppose, to impede. Okay, it's opposition to something. In this case, it's opposition to the movement of charges, opposition to the flow of current. So in simple terms, resistance is the capacity or the property of a material to oppose the flow of electric current. The circuit element that models this property is known as a resistor. Resistor is noted with R, and units is named after George Ohm, O-H-M, Ohm, noted by the Greek letter omega, uppercase omega. Uppercase omega. Okay, so R is the resistance in ohms, V is the voltage in volts. Volts is named after Volta. I believe he was Italian, V. And amps is named after amps is short for amperes. Amperes is named after ampere. Okay, so again, by far the most important element, the most important component in any electric circuit. We cannot build any electric circuit, even the simplest of electric circuits, without a resistor. Okay, even the simplest of electric circuits require a resistor. And the reason why is on the next page. So as voltage is applied to a resistor, and if you apply voltage to a resistor, current will flow. If current is flowing through a resistor, voltage will appear. And for a resistor, for a capacitor, for an inductor, these are all passive components. These passive components are governed by the passive reference configuration, meaning the current always flows from high to low, from plus to minus. So if you have a point in a circuit, resistor, capacitor, or inductor, it always goes from high to low. Higher potential to lower potential. Passive components like resistors, inductors, and capacitors, currents always going from plus to minus. For sources, it's exactly the opposite. For sources, current always goes from low to high, or lower potential to higher potential. Otherwise, our equations would never balance out. Okay. Current is like any other physical quantity. Water, because of gravity, will always flow from a higher level to a lower level. Temperature always moves from higher temperature to lower temperatures. Pressure, high pressure areas to low pressure areas. So any other physical quantity, current always flows from higher potential to lower potential. So keep that in mind. It's very important. All right, Ohm's law. I'm assuming you have come across Ohm's law in physics, perhaps? Yes, no, maybe. All right, Ohm's law. The most important principle and equation in electric circuit analysis. governs everything derived from electromagnetics. Simply stated, if current flows through a resistor, the voltage appears across it in proportion to the product of the current and resistance. V equals IR, I times R. Voltage is equal to the product of the current and resistance. There are many variations of this meme floating around on the internet. I like this particular one. Voltage is potential difference. Electric potential. Potential is potentially pushing charges because of the separation of charges. One end is higher than the other. So it's pushing the charges to go through a circuit. If there is resistance, it's opposition to the flow of these charges. And the equation that relates all three quantities is V equals IR. As an EE, as an electrical engineer, you have to become intimately acquainted with V equals IR because you would quickly need to find quantities depending on what you're given. If you're given voltage and resistance, you need to quickly find the current. If you're given voltage and current, you need to quickly find the resistance. So from the same equation, we rearrange the terms and we can find I is V over R and R is V over I. Okay. So that's Ohm's law. Let's see. All right, example one, quick and easy examples. I'm going to let students solve it and tell me the answer. So voltage is 1, current is 5. What is the resistance? Anyone? Yes. So I have 200,000 ohms. Anyone concur? You have a different number? You got one thumbs up. Anyone with a thumbs down? No one's head is going to be chopped off. Okay, got all thumbs up. Going once, going twice. And R would be 200 kilo ohms. That is correct. Quick and easy calculation. Now, when it comes to power, actually, let's go to the previous slide. We have V equals IR. What is the equation for power? P equals VI, product of voltage and current. Electrical power is always the product of voltage and current. So if you have Ohm's law, V equals IR, and you have P is equal to V times I, you can combine these equations to obtain two more equations. So if you have current flowing through a resistor, you can directly calculate the power. If you have voltage across the resistor, you can directly calculate the power. You do not have to calculate the other quantities. Okay. So if you combine these two equations, we can write P is equal to I squared times R, and P is equal to V squared over R. Again, these are also equations that you need to be very familiar with. After a certain point in time, like, of course, this is kind of like easy to remember. This is also easy to remember. This only comes with a bit of practice. Okay, so I squared times R and V squared over R comes with a little bit of practice. But I believe by the end of this quarter, you should, well, you may already be familiar with these. I don't know. But definitely by the end of this quarter, you will have these familiarized. Okay, I squared times R and V squared over R. So these is PR. Power in that resistor. You can use, you have both, you have voltage and you have current. So you can use either equation, right? You have voltage and you have current. You don't have to do anything else. Anyone? Five watts. Anyone else? I see one nod. 5 nods, 2 nods, going once, twice, and sold for 5 watts. 5W. All right. How about this one? Power is given, current is given. What is the resistance? Wait, PG is given, sorry. PG. G is generator or the source, so it's simply a label. You don't have to worry about the subscript. This book, this author is fond of using the subscript G for some reason. So G for generator, but simply it's a source. So the source or the supply voltage, VG, is not given, but the current IG is given, and the power for the source is given. Okay. Notice the power is given in negative. The negative simply implies that you are that it is supplying power. Because it is supplying power, minus sign. So a little bit more calculation required. Anyone? Anyone with a number for VG? Nope. What do we have? It's fine. It's not a quiz. You're not losing points or anything. Yes. Okay, so hold on. Let's start with VG first. Did you calculate VG? 200. How much did you get? 40. How much did you get? How much did you get? 40. 40. Yes. But the reason I'm asking about VG, I wanted to point it out. The power is for the source, hence it is given as minus. Okay, that's why it's given as minus 3 watts. Other than that, it doesn't signify anything. Okay, because it's supplying energy, so it's minus. So voltage VG would still be plus 40 in that sense. It's negative just because I, if you extend this I, that I is entering the negative terminal, so power is negative. For in general, all sources will supply power. So it's negative associated with the source and positive associated with the resistor. And then R, you said, what did you obtain? 533. How much did you get? Anyone? Front row? 533. Never omit the decimal point. 533.333. I like to go at least 3 or 4 decimal places. Chances of errors are minimized. And then PR. 21K. Okay. Let's see. R 75 milliwatts. Not quite. Yes. 3 watts, approximately 3 watts. So let's walk through the steps, okay? The point here is not to like embarrass students from speaking up. I want this to be a little bit of active learning process, okay? So VG can be calculated from the equation for PG. So power for the generator is VG times IG. So VG therefore would be PG over IG. And so we'd get 3 watts divided by 75 milliamps. So it'd be 3 divided by 0.075. Remember early on, I did unit prefixes going through that table. That's the reason. So I always like to convert everything and get rid of the unit prefix. So if there's a milli in there, I like to get rid of it. So milli is 10 raised to minus 3. So 75 into 10 raised to minus 3 would be 0.075. So 3 divided by 0.075 should give us 4040. R can be found from that voltage because it's applied directly to the R resistor. And so we have VG over IG and should arrive at 533.333. And then PR finally would be, you can use I square times R, or you can use V square or R, either ways. Okay, so use I square times R or V square or R. And you should arrive at 3 watts. Okay. So we're just starting slowly. Just want to make sure everybody's comfortable with the equations and calculations and stuff. This is the chance, not chance, but this is part of the learning process. Like we'll make errors, we'll make mistakes. Our calculations might turn out incorrect sometimes. I often make those mistakes when I'm in a rush. Again, this is a process of learning how to take it step by step. Okay. All right. So let's talk about series and parallel connections. Okay, series and parallel connections. In general, if you have two or more components connected together, they should share only one node between two of them. They should only share one connection between two components for it to be considered a series connection. Okay. So until you get to EE306, you will not be working with any 3-terminal devices. You'll exclusively working with 2-terminal devices. Whether it's a resistor, capacitor, or inductor, they only have 2 terminals on either side, right? So if you have an element A, B, C, D, and they're all 2-terminal devices, they have 1 terminal on each side. They can be considered to be in series as long as they share only one connection between the two of them and no more. And that shared connection should not have more than 2 elements connected to it. So the criteria for that is a shared connection between a 2-terminal device should not have more than 2 elements. Okay, so this is a shared connection between A and B, between B and C, and between C and D. That shared connection should not have more than 2 elements connected to it. And then we can call it to be in series at its outer terminals. okay, at its outer terminals. So A and B are in series, B and C are in series, C and D are in series, and so on and so forth until that connection might be broken. So we can state all of them are in series. Technically, you could have 1,000, 100,000, a million, a billion, a trillion components all in series, as long as they only share one connection each, and each shared connection has no more than two terminals of, two elements connected to it. Okay. So far, so good. Now, let's say we connect an element E here, right? So now, obviously, we have a third element connected. So C and D are no longer in series. So as soon as you see three connections at a junction, at a node, so this is basically, let's describe. Node is the junction of two or more connections. Okay. So electrical node is a junction of two or more connections. So as soon as you see three connections at a junction, then those elements are no longer in series. The C and D are no longer in series. But B and C are still in series. A and B are still in series. So we can say, first, when nothing was connected, the series connection went from A to D. Now it is going from A to C. So A, B, and C are still considered to be in series. Okay, even though that element is connected between C and D, A, B, and C are still considered to be in series from A, from the outer end of A to the outer end of C. Okay, so that's in series. So if you look at this example, which elements can you identify that are in series? Let's first eliminate the ones that have three connections. Which node has three connections? Yeah. Anyone? Okay, so B node, actually, you know what? Let's do this. Let's identify the nodes first. How many nodes do you see in the circuit? Let's start there. So let's count. 1, 2, 3, 4, 5, 6. Right? Do you all agree? It's good this is a beginning class, okay? It's a learning process. As you go along, you'll realize I have a lot of old dad jokes and I'll make fun. But it's not 6. The reason is because if you see a conductor or a wire between two nodes, they're electrically the exact same node. Okay, so right here you see a bend in the schematic, but that bend or that right angle does not mean anything. It's just a way of drawing that model. Remember, electric circuit is a model or a drawing or a schematic of an actual physical system. Physical system on your bench or in this room is going to look very different. So as an example, this wire right here, this cable is rolled up, but it's still the exact same electrical cable. It's the exact same conductor. So it doesn't matter how many turns it has, doesn't matter how many angles it takes physically, it has no bearing on the circuit itself. So again, this is not to like make fun of spoons or anything. I like to use this as a learning moment, okay? So it's an unbroken connection all the way here and all the way here. So we can say this is all one single node. Let's call this, node 1. This is 2. This is node 3. And this is node 4. Okay. Again, if you see multiple nodes in a circuit, the quickest and easiest way to identify is if you have anything connected between those two nodes. If there is no element except for a wire between those nodes, it is the exact same electrical node. Okay, it's no different. Right? So there are 4 nodes in the circuit. Now, if there are 4 nodes in a circuit, which node has 3 connections? 1 and 3, right? So 3 connections here and 3 connections here, right? You have A, B, and C at 1. And at node 3, you have E, B, and D, or B, D, and E. So right off the bat, we can say because it has 3 connections over there, they are no longer in series at that end. All right, at that end, they are not. However, at nodes 2 and 4, there are only 2 connections. If there are 2 connections, we can follow the pathway. So E and A until we hit a junction that has more than 2 connections. And in this case, we don't have to go far. We simply go from 4 to node 3, and node 3 has 3 connections, so it stops right there. Okay, so A and E are in series between nodes 1 and 3 because they're connected between 1 and 3. And then we can say C and D are in series between nodes 1 and 3. Okay. Does that make sense to everyone? It takes a while to learn everything. So again, that's why we have an entire quarter devoted to this class. Okay. And then while we are here, I just want to go on and finish up parallel connections. Okay. Parallel connections are like holding hands. Okay. Every element has 2 terminals, right? So if each element was holding 2 hands with the other element, then they're said to be in parallel, meaning they are sharing the 2 respective nodes correspondingly. So in this circuit, in this example, if you notice on the left, A and B are 2 terminal elements, and the corresponding terminals are connected to each other. Okay. They don't have any polarity, so I'm not going to mark the nodes as positive or negative, but both terminals of A and B are connected respectively to each other. And there is no interruption between the 2. Same thing happens on the right. You have D, E, and F. D, E, and F, 3 connections. All of them are in parallel. 2 terminals connected respectively to each other. It's 4 o'clock, so time is at an end. If you have to leave, you can leave. I'm just going to continue on with a little bit more, and then I'll stop. Okay. So similar to the series connections, parallel connections can have infinite number of elements, 100, 1,000, 1,000,000. Again, theoretically infinite connections. So say these are in parallel. and these two are in parallel. Yeah. As long as the connection is uninterrupted, meaning there is no other connection in the middle of that parallel connection, we say all of those elements are in parallel. So as long as they share the same two nodes, they're all in parallel. So if C was not present, if C was not present, then all of them would be in parallel because they would be sharing the same node at the top and at the bottom. Okay. That makes sense to everyone. Right? If C was not present, then A, B, D, E, F would all be in parallel because the connection would not be interrupted. Okay, we'll end class right here and we'll pick up here on Monday. There's no Friday quiz today, but there will be a Monday quiz. It'll be based on the material covered for the last 3 classes. Okay, so have a good weekend. I'll see you Monday.